Okay, this is video number 3, and we're going to finish up in this video. So I know that you're probably loving this chapter, but we're going to finish it up right about now, or in this video. All right, so environmental implications of minerals. So we talked about tailings in the last video. Obviously, with surface mining and just mining in general, we're going to have an area that has been destroyed if it's not fixed or reclaimed. And so what we need to do with areas that have been mined, and I mentioned the Superfund Act, with the Superfund where we take taxpayers' dollars and put money towards cleaning up old abandoned mines. But what should be done? What are the goals after a mine is done being used? And really, we need to restore, or the restoration of mining lands. And that just means to reclaim the lands when it's not profitable to continue to mine. So after we're done, we've extracted all of the minerals that we think that we could extract that's profitable, then we need to fix it and put it hopefully back into somewhat of its original state. So here's your little definition. So when I say to reclaim or restore the land, we're really looking at 3 goals here. First, we want to prevent any further degradation or erosion of the land. So we're going to try and prevent any more harm to the environment and to the land. Number 2, we're going to eliminate and neutralize toxic sources. So if we have some arsenic, lead, sulfur, we're going to try and eliminate and neutralize those sources so it's not running off and causing acid mine drainage. And we're going to try and repurpose the land. So it's great to put the land back to its original state, but if we can now make this into land that can be used, that would be awesome. And so I have a picture up here. First of all, you may not be aware, but the state of Florida is known for phosphate mining, and at the bottom right-hand picture, it's in your textbook, I believe. I know it looks like snow in the foreground, but this is really a phosphate mine, and we're basically able to get phosphate. We make the slurry or slush of it, and it goes to a processing plant. And as we've talked about before, phosphate is really important for our agricultural industry. So phosphate is used in fertilizers. So we need it for fertilizers, but we don't like it when it runs off from farmlands causing eutrophication. So we have to mine for it. We put it onto our crops because they need phosphate in order to grow and to survive. And so you can see this area on the right here, this is called derelict lands or derelict area. That means that it's been degraded by mining. And the way that we want to fix this is we want to kind of fill it in and plant the natural vegetation there. We need to do some research to find plants that are able to survive in this area, especially if the pH has been reduced. And so now, according to the law of 1977, we have the Surface Mining Control and Reclamation Act. It requires areas that are surface mined for coal to be reclaimed. And we talked about this. But the problem here is that there's no federal law for land that is mined for other things. So we talked about the Surface Mining Control and Reclamation Act for coal. But for our minerals here, it's not used for that. What's really cool about this picture on the left, you're probably like, why is there a golf course there? So there's this golf course, if any of you enjoy playing golf. It's actually in Florida. I believe it's near Fort Meade. And this is known as Stream Song. And what's super cool about it is that this is a former phosphate strip mine. So it was a former phosphate or a strip mine that was converted into a golf course. And I've never been there, but I heard that the golf course is really cool. It's got a lot of hills to it. Any low-lying areas kind of collected water, and so now they're bodies of water that I guess you have to kind of avoid if you're a golfer. It cost $80 million to convert that phosphate mine into the golf course. And so native grasses are growing there, and I've heard that it's one of the nicest golf courses in the state. I think it's also pretty expensive to play there. So that would be an example of restoring lands that have been mined. So it was once a phosphate mine. Obviously, it takes a lot of money to make it into a usable piece of land, but it can be done, and we saw it with this example. Okay, so some creative approaches to cleaning up mined areas. First of all, using wetlands. So I know this sounds like kind of interesting, but instead of just like, trying to like physically remove um, any of the heavy metals that are associated with these mines, we can actually set up a series of wetlands. And we talked about some of the ecosystem services of wetlands in the past, but basically if we make a series of wetlands, they'll help to trap sediments and pollutants, and they can also neutralize water. But it's really expensive to make these man-made wetlands. You can kind of see a picture in the top right-hand corner there of like some of the piping that needs to happen. Um, but we can make a series of them downstream from the mine. It has been designed and tested to work with mines. We have found bacteria that are able to consume sulfur, so that's pretty cool because it could make the water less acidic. And yeah, this is just one of the examples. And just to remind you of some of the ecosystem services and how they work, they definitely could be used to clean up water here. So you can see some of that dirty water dissipates from upstream and it goes down into the wetland. And the wetland kind of is going to absorb some of that water. It's going to saturate down into the ground. And you'll have bacteria living in there, breaking down many times organic contaminants. And some filtering happens here. You have some bacteria living in there, and the water that ends up leaving a wetland is much cleaner than the water that enters a wetland. Your next one is called phytoremediation. You've seen this before with the soil chapter. Whenever you see the prefix phyto, you should think plants. So phytoremediation uses specific plants to absorb toxins. So this is pretty cool. Specifically, to give you an example, the twist flower, I believe that your textbook talks about the twist flower. Here's some pictures of it. And it is a hypoaccumulator. And basically, it's going to store some of this nickel into the cells, and we can find an area that needs the removal of nickel and heavy metals. Plant the plants. The plant is going to absorb that heavy metal, and then we have to dispose of the plant. So obviously the plant's not going to live there forever because you don't want any of those heavy metals moving through the food web and the food chain. But after the area has been cleaned up enough, I guess, or to the point where soil scientists think that it's reusable, then the plants will be removed and they can either be sent to a hazardous landfill, and we'll talk a little bit about those later on, or they can be incinerated. So we can use specific plants to remove some of these heavy metals from the soil. So it's pretty cool. Another creative approach versus just mechanical processes of removing the soil. And then I also have a picture of manure up here. So cow manure can also be used. So we could take a whole bunch of cow manure because what else are we going to do with it? And throw it onto areas that have a very low pH, and there's lots of bacteria that live in and around the cow manure that will help to increase the pH. So it helps to reduce some of those acids, to kind of neutralize those acids, I should say. Okay, an international perspective. We've discussed this before too. Again, that's why I picked this chapter that I would give you the video on, because I knew that you guys would already know this. So we talked about mineral reserves and resources. So again, make sure you know the difference. I know it can kind of be confusing, but a reserve is a mineral or a pocket of minerals or a place where we found minerals that's profitable to extract today. We talked about the same thing with coal. So a reserve, we've identified it and we are able to extract it today. A resource, we know it's there, but you know what? Right now it's not profitable to extract. So maybe it's too deep in the ground. Maybe we have an abundance of that mineral. We don't need to get it out of that one place. So a resource and a reserve. When we combine all of the mineral resources and reserves together, it's known as the total resources or the world reserve base. And resources and reserves can actually change like from one category to another. So we could talk about anything. Just to give you an example, because we mentioned, aluminum before. So let's say that we have aluminum, and we have a whole bunch of resources of aluminum. If we have an improvement in technology, the aluminum resources will change to the reserve category. So that's something that's good. It's like, oh, we have better technology. We're able to extract deeper into the ground. Politics can also change minerals from one category to another. So if we have an area that maybe at one point, hold on one second. Okay, sorry about that. Um, so I believe I was in politics. Politics can also um, reclassify or change minerals from one category to another. So if there's some political unrest in a country, it could, and minerals are found in that country, it could change that mineral category from a reserve to a resource. So it could actually become, or will have less availability to it. So it could change it into that direction. And economic, so if the price of a mineral on the market drops, we're not using it because maybe we found a substitute for that mineral, then we can have that mineral move from a reserve category to a resource. So it's not maybe profitable to extract because now we have, I don't know, plastic or ceramic or something that can be used in its place. So note that minerals can move from one category to the other um, due to changes in technology, political unrest or politics, and economics. Okay, so this is a graph from your textbook, and it is showing you North American consumption of selected minerals. You can see U.S. and Canadian consumption as percent of world consumption. And so you can see some of the minerals that we use the most in North America. Just some other little facts for you. The U.S. and Canada, we have about 5% of the total population, and we consume 25% of the world's minerals. Um, China, as you could guess, as they are moving through the demographic transition model and becoming industrialized, they are consuming more and more minerals. And they use about 20% of the world's aluminum. So some of these countries that are moving through, they're continuing to use more and more minerals. In some countries, like South Korea, for example, in the 1950s, they used to export iron and copper to other countries, and now because they have become industrialized and they're moving through the demographic transition model, now they have to actually import some of those minerals. Okay, will we run out of minerals? That's always the question. Same thing with fossil fuels. Are we going to run out? And if we are, when are we going to run out? It's really difficult to assess minerals in the future. So in the 1970s, we were using way more than we had ever used before as far as minerals. And we thought that there would be a major shortage by today. We thought we wouldn't really have much of this left. Again, it's non-renewable. But, and you'll see on the next slide, I'm kind of getting ahead of myself, there's a bunch of reasons as to why we haven't run out. And like I said, I'll show you that on the next slide. So here we just have some selected minerals and life expectancies, and you can see the amount. Let's look here. We have lead. Looks like we don't have as much, whereas maybe aluminum or bauxite, we have a decent amount. But as I was just saying, and maybe I skipped the slide. Hold on. Okay. I just went back a slide. I may not have it written down on a slide, but I know I have things that I need to tell you about why we haven't run out of minerals. So as I was about to say, we do have some substitutes for some of these minerals. So think about it with plastics and ceramics. So in the 1970s, we didn't realize that we would have these things that we use as a substitute or to replace some of our minerals. So we haven't had to use the minerals as much as we anticipated. New discoveries. We're always finding more minerals, especially we found a lot of iron and aluminum. We recently found that in Brazil and Australia. And also we went through some global economic slumps, so that also decreased the amount of minerals that we ended up using. Okay. So locating and mining new deposits. So many mineral deposits we haven't exploited yet, probably because they're places that we're not trying to mine, not quite yet, not until we run super duper low. But some of The reasons here why we haven't exploited them yet is they're difficult to access. If you look at the bottom right-hand picture, we have a picture of a tropical rainforest, and think of Indonesia. Under the thick forests with all of the mosquitoes and the malaria in the rainforest, we believe we have significant deposits of minerals. But currently, we don't need to necessarily cut them down. It'd be difficult to get to them. So as of this moment, we have not exploited those minerals. For the insufficient technology, kind of goes along with located too deep. We believe that we have mineral deposits in polar regions. So up in the North Pole, where we have to use special technology to break through that ice. We don't really have that technology yet, those rigs to break through that very hard ice in order to get to those minerals. So not the best technology at this point. Even we can say some less developed countries, they have incomplete geological surveys. So some areas, they don't even know what they have underneath them. So all of these are basically reasons why we have not exploited all the possible minerals. So many known mineral deposits have not yet been exploited because of technology. Let's look at the ocean. All right, so minerals from the ocean. So we can extract minerals from seawater. There are a lot of dissolved minerals, in seawater. Think table salt, bromine, magnesium. All of these minerals are easy to extract from seawater. We also believe that we've kind of lost, I guess you could say, many minerals to the ocean floor, or to the seabed, as rivers kind of drain into the oceans. Do we really want to remove those minerals from the bottom of the ocean? Probably not, at least not now. That could cause a whole bunch of environmental problems on the bottom of the ocean. Think about all those benthos that are living down there. So we really don't want to extract minerals from the bottom of the ocean. And then the picture you probably see on the right there are known as manganese nodules. So these are actually on the ocean floor. These are rocks that contain manganese, cobalt, and nickel. They're mostly found in the Pacific Ocean. We believe that there's about 1.5 million tons of these nodules, or basically rocks. You can see a picture. How are we going to get them? If we want them, you're like, wait, what do we need manganese for? Just to give you an example of a product that has manganese, a lot of our stainless steel. And as you probably know, stainless steel is very popular right now, especially for appliances. And so if we wanted to get these manganese nodules, we'd have to dredge the ocean floor, meaning that we would have to take some nets or some shovels and kind of rip up all of these manganese nodules from the floor. We're not going to go down there and scuba dive and pull one by one by one. We'd actually have to do it in a large amount. And that doesn't sound very good. We don't want to dredge the ocean floor. And here's where they're located. You can kind of see in the Pacific, off the coast of, I don't know, California-ish. The U.S. and other highly developed countries, we've already staked claims on these manganese nodules, but we don't think it's quite feasible just yet. So maybe in a few decades, we'll start to mine these for profit. But obviously, all of these countries are keeping their eye on these manganese nodules. All right, so advanced mining and processing. So we said that in order to get these minerals, we have to mine, so surface and subsurface mine, very destructive to the land. Overall, if you ever had to come up with an environmental problem, it just decreases biodiversity. The process of smelting, it's going to add air pollution to the atmosphere. If we don't use air pollution devices, we end up with tailings and slag, and so it's obviously not the most environmentally friendly thing that we could do. So ways that we can kind of use new creative methods to mining and processing these minerals. And the first one you have here is biomining. And so biomining uses microorganisms, you can see that thiobacillus in the bottom right hand corner, to extract minerals from low-grade ore. So it's pretty cool. What we do is we can add the thiobacillus with some sulfuric acid on the ore, and we'll have a chemical reaction that can actually leach copper. So biomining can be used to get copper from that rock that doesn't have a high percentage of copper. So can be used for low-grade ore. It's also been shown to recover gold. So we've seen a 91% recovery of gold when we use biomining, so that's pretty cool. And so mainly done in bacteria, and used for copper and gold, so as I just mentioned. So pretty cool creative approach in which we can um, get some of these minerals from low grade ores. Okay, so finding mineral substitutes. So as we've stated, that minerals are non-renewable, meaning that once they're gone for good. We're going to have to look in the future for using some substitutes. And sometimes they can be expensive, but here's some examples of substitutes that we can use in place of some of these minerals. So plastic, glass, aluminum has been used in place of tin. We could use maybe some glass fibers instead of copper for telephone cables. So it's really important for the future that we are going to invest and we're going to research some of these new substitutes in order to take the place of these minerals, some of them that are scarce. And the last slide is about mineral conservation. The 3 R's, super simple. We will revisit this again, but we know reduce, reuse, recycle. I've told you many times, please note that specific order. Reducing uses the least amount of energy. So reducing the fight the gotta have it and throw away mentality. If you buy something, if you are basically buying something, you want to look where it has the least amount of packaging if you're trying to reduce, for example, the amount of plastic or just the amount of minerals that you're using. Reusing, obviously this is super simple, reusing the same product over and over again. Some good examples, refillable water bottles. So instead of maybe using like aluminum cans for soda, I don't know, buy a big 2-liter plastic bottle of soda and you fill up your cup, even though you shouldn't really be drinking soda. And recycling. So of the 3, I've said that this uses the most amount of energy. So we're going to take something and we are going to make a new product out of it. Many times it's going to use a lot of energy, water, new materials. So of the 3, it's the worst, but it's better than throwing into a landfill. And the process of dematerialization. So over time, many times we've seen products have less and less stuff in it. So awesome example, let's see, do I have a picture of a water bottle up here? No, I don't. Something that we've seen in recent times are like the water bottles. So we used to have plastic water bottles. I don't even know if they say them on it anymore, but now they kind of say like uses, I don't know, a certain percentage less plastic and paper. So they're trying to reduce the amount of plastic that's used in a water bottle versus what it was used before. You can think of cell phones, computers, all of these have gone through the process of dematerialization. So this is a way that we can conserve minerals, is by making new products that are going to use less minerals. And so one important key concept about dematerialization, though, the only thing that's like a little bit confusing is that the new product has to be just as good as the old product. So for water bottles, some of them are a great example of dematerialization while others are not. Because if you look at some of those water bottles that have less plastic in the cap and less, I don't know, plastic in its actual, like, itself, and it doesn't work as well, let's say it leaks all over your bag when you bring it to school, then you're not going to use it because it doesn't work well. So the new product has to work just as good as the old product. And I'm sorry for talking for 23, almost 24 minutes. But I hope that this was helpful. Please read your textbook. Don't forget to read your textbook, read your textbook, read your textbook, so that you will be prepared for Friday. So again, the quiz star will be open on Friday through Monday, or sorry, excuse me, Sunday. I will close it down at 11:59 on Sunday night. Do not start your quiz star at 11:30. Do not start your quiz star at 11. In fact, get it done with. Get it done nice and early so you don't have to think about it all weekend. You can do it on Friday when you come home. Get it out of the way. Also, your reading guide is due Friday night at 11:59 onto Google Classroom. I hope you guys are having fun.